I'm Robert Vandermeulen, and this is on the geometry of human and neural network representation spaces. This is like a nice little line of work done by a lot of people on various papers. We have Google, National Institute of Mental Health in the US, TU Berlin, and some other folks. Really, the main character here is Lucas Mutenthaler, who is the first author on a line of papers on which this is based. Okay, so to begin, this talk is going to go over sort of three questions. How do humans recognize and organize concepts mentally in their head? What is similar? What is different? How can we formalize such a thing? How do these representations compare to neural network representations of objects? And how can we realign neural networks to be more human-like? And does this bring any benefits? It's all based on these three papers. So it's a nice little bang, 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 a few nice papers, and one leads into another. I would say the beginning of this talk is a little bit more academic, and it is strictly increasing in practical importance as the talk goes on. Okay, so to begin, how do we collect and geometrically represent human concepts? So this whole talk is going to be based on a data set called the things data set. It contains a collection of 1,854 object concepts, and for each of these object concepts, there is a collection of representative images. Object concepts are unambiguous objects. So for example, we have suit, flamingo, car, bat as in a baseball bat, and bat as in an animal. These are in the things data set. Not in the things data set includes concepts like equipment, night, stuff, or winter. It's really hard to have a picture that encapsulates winter. And this whole data set was chosen so as to have a data set, a collection of nouns and images that one can use for studying cognitive science problems. So some quick examples. These are truly from the data set. We have banana, we have blowgun, and we have chandelier. So yeah, this is sort of what we're looking at as far as the things data set goes. And by the way, if anyone has any questions about any of this, feel free to interrupt. If people get confused now, it's not going to be good for me to keep going. So please just interrupt if you and your neighbor agree something is unclear. Okay, so we have all of these objects, and we want to devise some way to collect information from humans, and using this information, determine what objects are similar and what dimensions and so forth. And to do this, we don't use this, the things data set people did. They use the odd one out task. In the odd one out task, you present a human subject with k images. I've only seen k equal to 3, but it's possible it could be greater than that. And the subject decides the object that fits the least, or the pair that fits together the best. Yeah. So here, we'll do one really quickly. Everyone here can participate. So here are 3 objects: cactus, caviar, and champagne. Does anybody have a guess as to what 2 objects are the most similar here? Go ahead and just... Okay, 2 and 3, you don't have to speak. I would agree with this. These are the most similar. Caviar and champagne you can ingest them. They're fancy, but there is no correct solution. So the whole point of this is just to collect responses from human participants so we can get an understanding of how people organize objects mentally. Okay, so the things data set contains 4.7 million triplet responses. Every triplet was randomly selected, presented to a subject, and repeated. This was done online. It's all open. I'll show the website in a second, but there's data sets for training and testing if you want to dig into this a little bit. It contains over 12,000 participants. And for a randomly selected collection of 1,000 triplets, they repeated and presented these triplets to multiple different subjects to understand variability. So basically for some triplets, it's not obvious like what the correct answer is. The best I could come up with was chandelier, stapler, and suit. I wouldn't know which one of those fits the least, but yeah, there's some variability among participants. And so for each of these 1,000 responses, these 1,000 triplets, they were presented to 25 different participants. And this way you can get an understanding of what consistency looks like in this triplet task. And using this, we can get a very good estimate of the upper bound of the ability to make a classifier that correctly classifies what a prediction would be. In particular, like given a random triplet and a random subject, what's the best you could do? What's the best accuracy you could get for predicting what that subject would predict? And we get 67.3. Yeah, and this number is kind of interesting. It's maybe not as high as you would think it would be, but random guessing gets you to 33%. So there's a lot of consistency, but there's also quite a bit of noise. Yeah. And Things has a lot of other types of data. So there's like recordings, like EKG recordings, or ECG recordings, and various other things, all going towards this idea of making a nice data set for cognitive science. So check it out. It's at thingsinitiative.org. Okay, so we have these responses. What do we want to do with them? I'm going to pretend that each object has a number associated with it just for convenience. So for each object, we would like to create a vector that's d dimensions that somehow encapsulates this object. And we want xi to be near xj if they are similar. How do we model this? So we will have this similarity of a pair of objects be the inner product of the two object representations. And we will model the likelihood of choosing a pair AB from a triplet IJK, like via softmax, essentially. So we have here at the top is the probability of choosing AB from IJK in a triplet problem from our model. Okay, like if anyone has any questions, we're going to be using this for the whole rest of the talk. So please, if anything is unclear, speak now.
I mean, the question is, an object in our concept is invariant under lots of transformations. And in what way does this reflect, for instance, in the embedding vector?
So this is a good question, so I can highlight the point. So these embeddings, they have no access to the image directly. It's only being estimated through human responses. So this xi, xj has no, it's not being generated from an image. It's being generated solely through human responses. How would a human viewing different transformations? I'm not sure. We'll get to that later, though, how computers interact with this and so forth. Okay, so one could estimate x to be a maximum likelihood. And we want x to predict human responses well, but we also want x to sort of reveal which dimensions are important when humans find things to be similar or different. So like, what are the fundamental properties humans find important when categorizing subjects in their head or objects? Okay, so I'm going to go through this quite quickly because the latter part is more interesting. So the initial estimator for this is called SPOS, and this is a friendly competitor. This person's involved in other papers of ours. So in SPOS, we enforce x to always be positive, and this is sort of based on the cognitive science concept that objects tend to have properties and not really have negative properties. So for example, negative wood doesn't make sense. Sometimes there's clearly like a property and its opposite, but usually like something is metal and you don't really want to say it's very, very not metal, for example. This also uses L1 regularization so that we get a sparse representation. So it's pretty straightforward here. And then D, this encourages representations to be sparse. And this is nice because most objects only have a few significant properties. And here's the entire loss for suppose. It's a nice maximum likelihood estimation problem with L1 regularization. Okay, so our method is Weiss, and this is our first contribution, but this is more to like set up for the rest of the talk. We use a variational Bayesian approach to this with a slab spike prior to get sparse representations. So here's a prior, and I'm not going to go much into the details here. So it's Bayesian approach. And then the posterior is modeled via Gaussian distribution using variational Bayes. So we model the posterior like this. And here's the entire loss. Again, I'm just going to go through this quite quickly. And then when we're done, we use the mean of the posterior as a representation. So basically, this is just a nice alternative to SPOS for getting these estimates, and we'll show why that's nice in just a sec. So both of these have similar accuracy on various data sets. So these are other data sets. You can probably figure out what they're about, adjectives and food, also with a triplet task, but we see that SPOS and Weiss get approximately the same accuracy on things. In fact, we know that it's no statistically significant difference. But where it is nice is on other metrics. So Weiss finds fewer dimensions for its representation. So we can see here 44 is less than 52. So this is good. You're having more meaningful dimensions. And Weiss is also much more likely to recover the same dimensions. So if you run these methods and your dimensions just look different every time, like there's no consistency, there isn't a sense in that you're getting sort of the true underlying properties of your object concept. Ideally, like you come up with the same dimensions that are very important for understanding similarity. And so Weiss is better at this. And the best thing Weiss is good at is sample efficiency. So if we only use 5% of the things data set, SPOS basically doesn't work at all, and Weiss works pretty decently. So this is just accuracy here, and there's the upper bound. So it's sample efficient. That's nice. Okay, so let's get a little bit more interesting. What are the dimensions that humans find important for understanding objects? So these are all, again, enforced to be positive, and dimensions where the average magnitude is higher are more important. So I can sort all the dimensions by their average magnitude. So dimension 1 has the highest average magnitude. Dimension 44 has usually the smallest magnitude. So what do we get? So here's the first 6 dimensions. Dimension 1 is metal. I would call it that. I don't know. Metal or a tool or something. Dimension 2 is maybe food or carbs, the best kind of food. Here we have plants. This is maybe animal, with mammals being like the most animal and things like lizards being less living in some sense. So these are the objects that have the largest value for these different dimensions. So we don't see like a gradient as we go down this ranking. Here we have maybe domestic or furniture, and this is clothing. Okay, and just in case you're curious, because I think this is pretty neat too, here's some other examples of this. So from things, this is like dimension 17 or something: fire, wood, color. And food, remember Weiss had 5 dimensions. Here's 4 of them. I would say greasy, vegetable, fruit, carb. I don't remember what the 5th one is. And for adjectives, we have some common things here like size, and like this is probably like a bad dimension and so forth. Okay, so that's it for the first part. Takeaways are the triplet task is interesting. So there are a lot of benefits to this compared to other ways of collecting data like this, like the Likert scale, or like arranging objects so that similar objects are near each other. It's useful for something like recommender systems. So like it's a natural way of collecting data from people, including like general expertise collection. So Perhaps you want to do some sort of unsupervised learning from an expert and give them a simple task to do. This is a way to do it. And Vice has good sample efficiency and representation consistency. Okay, so step 2, how do Vice dimensions compare to your representations from neural networks? So what's going to go on here? So we're going to take a neural network and we're going to take an image from things associated with an object concept. So this is object concept I. We're going to pass it through a neural network and we're going to use some representation from the neural network as the neural network's representation for this object. We will use the logic layer representations just because that worked the best. It's typical to use the penultimate layer for transfer learning, but everything just sort of was more aligned at the logic layer. So that's the layer right before the final softmax. So we went with that. And here we will determine similarity via cosine similarity instead of inner product. And again, this is just because I gave the most benefit to the neural network. We investigated quite a few neural networks, a lot of different kinds. So we can see we have, well, a lot of different models, different architectures. We have different data sets. So we have like image text models. We have like really massive, it's later. Yeah, we have a lot of ImageNet 1Ks. We have self-supervised models, different kinds of losses. And we also have like, here's JFT3B. That's a big proprietary data set at Google. So, and like this is a massive supervised problem, or massive supervised data set. Yeah, so there's a lot of different stuff in there, and we can explore sort of what patterns do we see and so forth. Okay, so first we're going to look at zero-shot accuracy using the same similarity model as before with cosine similarity. How well do neural networks predict responses from humans using the images from the things data set? So here's the first, I don't know. So this paper is just full of graphs and stuff. So I just kind of chose stuff that I feel like had the most interesting message, but there's a lot of different ablation studies in here and so forth. So here we have ImageNet accuracy versus zero-shot accuracy or zero-shot auto and out accuracy. And we can see that it is only the slightest bit correlated here. You're going to be seeing a lot of images or a few images like this. It's worth like looking at the dots and what they represent. So we have image text models are these purple dots. Supervised ImageNet 1K are these sort of like peach colored crosses. JFT3B is up here, so it's doing quite well generally. And we have self-supervised are these sort of crosses like that. So ImageNet accuracy is not correlated with alignment of representations to humans. Like the objective you use makes essentially no difference. And the architecture you use makes essentially no difference. So basically, like, you can't really make a design choice to make your network more aligned. Just like if you have a data set on a problem, you can't be like, oh, if the network's really deep, it will be more aligned. Or if I use like a image transformer or whatever, it makes no difference for alignment. Continuing on, we see that self-supervised models are not well aligned. This is probably not too surprising because they have no concept of similarity for images in a way that means something to humans. Image text models get worse aligned as you increase ImageNet accuracy, which is weird. We'll get back to that later though. And we can see that, like model size makes no difference. Again, like you can't really make like a design decision in your architecture or training method to improve human alignment. Okay, so what properties do neural networks understand? So for a trivial IJK with A and B selected, we could consider the dimension that has the largest contribution to this inner product. So it's the argmax of the index in this inner product, which had the biggest contribution to why why it was chosen that way according to Weiss. We might call this a significant dimension for a triplet. And we can see how accuracy depends on a significant dimension, and thereby understand what concepts neural networks are naturally aligned to after training. So here are 4 dimensions: animal, vehicle, and sports. And here's some raw zero-shot odd one out accuracy. So here we see the animal dimension is, well, it's better aligned than the other ones, and we see that the image text models are quite well aligned here. Self-supervised stuff is not doing so great. We see that the image text models don't really understand vehicles, and they do get sports. There's many graphs like this. It's really something you can dig into in the paper. But this sort of leaves an open question, like maybe these dimensions aren't naturally coming out in the representation, but maybe you can kind of dig it out of the representation. So we consider linear probing. Can we adjust the neural network representation to be more human aligned? So what we do, this isn't so important, this is for a previous talk, but we randomly split the objects into 2/3 and 1/3, and we train the neural networks for linear probing on triplet problems for the 2/3, and we test on the 1/3. So you really lose a lot of, so objects that were aligned during training are never tested on at test time. So it has to be transferred between different object concepts. So there's no like leakage happening in the data here. It's an expensive way to train things because you lose a lot of data by doing this. So basically 2/3 of the objects are used during training and only 1/3 are used at testing. And so you have to throw away all objects, all triplets that had one from one set and one from another one. Okay, and so now we have a new representation. So W is this linear transform. We have a new representation, and Y is now from the penultimate layer. And again, this is just because this is what sort of got the most interesting results out of the networks. Okay, and we repeat this several times, and there's significant data loss. Okay, so what happens with alignment? So here's the original zero shot, here's probing, and here are the accuracies. So we see that everything benefits from probing, probably not too surprising. The main thing we see here is that image text models are winning very clearly now. They outperform everything. Image text models have the most deep understanding in a human-like way of all models. And yeah, I don't know, there's not too much more to say about it. I forget what these 2 blobs are here. And then we have JFT3B. So this is the biggest problem with the most data and like very nice labeling. And this is the best aligned afterwards. And this at the top again is what we know to be the Bayes optimal classification. Okay, some interesting things about this. So there are other ways of testing, of like collecting human alignment, like the odd one out task. There are other tasks like this that other people have looked into, and we can test to see if aligning to our triplet data sets naturally aligns the network with other tasks, like other people have collected this, and indeed it does. So this is some evidence that there is like a baseline true alignment of neural networks to like how humans conceive things that does not depend on how you get that information out of the human. We see that linear probing is domain specific, so like how effective it is really depends on the dimension. So remember the significant dimension thing from before. Animal this is from before probing. After probing, we're getting nearly 90% accuracy from some of the networks. So like the animal concept is really very deep in these networks. And we can also see that the image text model almost always moves out in front of the other classification models via linear probing. Just more evidence that really like image text models are have the deepest understanding of the world, which to me isn't too surprising. And JFT3B is almost always near the front. Okay, and this again, zero shot odd one out accuracy, and this is for each of the 45 dimensions, and we named all of these. And I can just go back and forth. You can see like the most important dimensions. There's quite a big performance bump. Here, there's like a bit of a mix of different kinds of models. But now at the top, there's lots of image text models and so forth. A couple of interesting dimensions, I think, are animal, where we get really good understanding. So this appears to be what is best understood by the networks deep down. And this is what we call the royal dimension. And this is like fancy things like crowns and goblets and like mirrors with gold on this side and stuff. And this is a concept not understood by neural networks very well, fanciness. So I don't know, maybe they're very communist or something. Yeah. So there's a lot of other results. I would recommend looking at it yourself. It's hard to know what you'll find interesting, but like there's a mountain of graphs in there. I was sure you'll find some stuff you like. So takeaways, lots of results. Best naturally aligned neural networks are generally simple networks trained on classification. Richer networks, you can get a more aligned representation out of that, but it has to be extracted. And training data set and task is the most important. If your network is rich enough to do well at this task, it doesn't matter which network you use, like its alignment will be consistent. Okay, so with this probing, does that improve our network performance on like useful tasks? Like this is a natural question to ask, I think, and it does not. So this is a little surprising. We really tried hard to find some tasks where it improved performance, where it was sort of like interesting to report. You don't want to report disinteresting things. Tried classification, fusel learning, anomaly detection, and other things. Actually, the degradation is quite bad in performance for the most powerful networks. Although we did see a bit of improvement for networks that didn't do very well. Sometimes you got a bump in performance. But it's not very interesting to report that we're able to get badly performing networks to perform slightly better. So why is this happening? So probing modifies the global structures of the representations like quite strongly. So the nearest neighbor in embedding space changes drastically. So we can throw through 50,000 ImageNet images, and with each image, look at its nearest neighbor and see if this changes after probing. And with the naive probing, 85% of the time, for 85% of the points, it had a new nearest neighbor, which is kind of crazy. So almost like locality is just kind of destroyed via doing this. So for example, here is an image from ImageNet. It's a dog. It's kind of hard to tell, like a terrier kind of dog. So untransformed, these are the nearest samples where each sample is from a different class. So we find the nearest sample, figure out what class that's from, then find the next class that has the closest sample to that first point. And as you can see, it's all dogs and all kind of terrier-like. Here's what happens if we do naive probing. We got a dog, that's good. I think that's like a baby wolf, a Shiba, a beaver, a weird dog, meerkat, a cat, yeah, a fox. So already it's really destroying sort of like the dog understanding inherent in the network. And like, remember, there's many dog classes in ImageNet. So like there's a lot of information about the subtle differences between dogs, but that they're all similar in this, in the network trained on ImageNet. Okay, so yeah, so things contains a lot of salient information about what I would call like the global structure of concepts, like that cats are similar to foxes, kind of, but not so much on fine-grained topics. So like two different breeds of cat, it has no notion that different breeds of cat are similar to each other. Like this isn't inherent in the things data set. There aren't multiple breeds of cat as object concepts. It's just cat. So, but this is encapsulated in ImageNet or image text models. They have a lot of detailed information. There's like a lot of detailed understanding on images in such a model. And so we need to preserve this locality while adjusting the global structure. And so to do this, we introduce two losses, the global and the local loss. I'll get into that in a sec, but this image is sort of showing what needs to happen. Like the local organization of these different sort of groups of related concepts are actually good, but we need to sort of rearrange them globally so that, like, you know, animals eat food, so animals and food should be kind of near each other. Like with just straight up ImageNet training, there's no reason why apples should be closer to cats than rocks or something. Like there's no high level understanding of what's going on. Okay, so I'm going to go into the two losses now. Just to remind you, WY is a transform concept, and it is now from the penultimate layer. Okay, so the first loss is we do not want W to be too far away from the identity. So basically, we would like to not change the initial concept too much, and that's pretty easy loss to add. So basically, it's this. You want to find W where it's close to some scaled version of the identity, and scaling the identity is not a problem because your network's naturally going to want to push out its outputs to large magnitude because of softmax and the cross entropy loss. So we don't care if W is scaled, but we'd like to keep it close to identity. And it's a nice little trick. You can show that that's equal to this. Fun exercise. It's also in the paper. Okay, we also introduce a local loss where it tries to preserve nearest neighbors. So we can imagine you have a network. We throw through the embeddings of all ImageNet samples and put them into this data matrix. And we can have a similarity matrix constructed via the cosine similarity of all these embeddings. And then we can consider the same thing with probed embeddings. So we have this other similarity matrix. And what we want to do is basically keep these looking similar. And we do this via a cross entropy kind of loss. There's a little bit more going on here. These are actually like special row-wise softmax functions. But basically, we would like this distribution similarity to be similar in a sort of softmax and then cross entropy kind of way. So the final loss looks like this. Global, this is to train, this is to realign things, this is to preserve locality, and this is to keep things near the identity. And indeed, we found that removing either of the other two losses hurts performance later. We call this the glocal loss. And indeed, it does preserve nearest neighbors. So here we have some graphs showing, basically it shows how close the nearest neighbor is preserved after the transform. So after the transform, how often is the nearest neighbor, the previous nearest neighbor within 10 nearest neighbors of the new transform? And you can see here, the naive destroys this quite a bit, but now we're back to having like locality preserved via nearest neighbor. That wasn't super clear, but it's keeping things locally more structured. Okay, so where is this useful? We found a few nice applications of this. We need tasks where the global structure is really important. Dataset shift is good for this because you need to have a good high-level understanding of sort of like how objects are similar and different. Another thing that's good for this is few shot. Like I can show you one picture of a cat, and then I can show you a cat or a dog, and you won't need many examples of the initial cat to know that the cat is more similar. Whereas a network, maybe you have to give it many, many samples so it has something to generalize from, but we have a good understanding like globally of what objects are similar and different that we sort of understand as a community. Okay, so for this experiment, and yeah, we use multinomial logistic regression. to fine-tune these. So few shot means 5 samples. So here are the networks we use. This is Wikipedia, Lion, so forth. So entity 13, this is a data set from breeds. It's a data set that has a lot of data set shift. And we can see that the global loss improves things quite a bit, 6% more accuracy here. Entity 30, which is another breeds data set. Global is doing the best again. CIFAR 100 course, so this is using the course CIFAR 100 classes. Again, our image text models are doing the best. And for regular old CIFAR 100, it doesn't do the best anymore. We really kind of need this sort of global structure to be part of the problem that we're interested in for this to improve things. There's Sun 397 and DTD. I'm not going to get into those, but some cases where it's not so clearly winning. All right. Another example of a good problem for this sort of global structure is anomaly detection. So in anomaly detection, you only see examples from one class. That's it. And you need to determine if something is unlike that class that has been presented to you. So this is really quite dependent on your initial structure. Whatever you have at the beginning is how you're going to determine whether things are similar or not. Yep. So again, we have similar models. And this is CIFAR 10, one versus rest. I'm not going to get into this. It's a standard anomaly detection test. Again, we are doing the best. We're doing the best again for CIFAR 100 and for course CIFAR 100. So anomaly detection, this works really well. And there's what's called the ImageNet 30. It's the follow-on to the CIFAR 10 one versus rest test. And we do very well there again. Okay. If we include dataset shift into our anomaly detection task, then we just win, period. There's nothing even gets close to us. Oh yeah. It's worth noting that this sort of improvement only happens for image text models. We don't see this for models trained on ImageNet. But these work better than the ImageNet models, so this is what we're interested in anyways. Okay, and just to finish this up, some other fun and interesting observations from this. Is alignment universal? So for each of these tasks, we had different hyperparameter training. It's all very reasonable, trust me. There's no trickery going on in there. But is this alignment work cross-task, or are we sort of learning a different thing for each task as far as this alignment goes? And indeed, we can see, so here's anomaly detection, performance, and few shot classification. We have strong correlation between these two. So we have different kinds of training. So this is CLIP versus ImageNet. We have original naive probing and global probing. So up here is original or global. Yeah, so it's working. And naive doesn't really help anything. And indeed, this correlation is quite strong. How much does regularization reduce alignment? So the probed networks are the most aligned, but how much less aligned is a network using local? And so we have here, this is the original, the dots are the original. So yeah, here's our performance in few shot. Here's human alignment. We have our original representations, naive and local. Don't worry about adversarial for right now. Naive all perform poorly on few shot, but they are just slightly more aligned than the original or the naive. And we can see that, global is almost as well aligned as the naive probing, but not just slightly worse. And we get something similar for anomaly detection. It's going to go kind of quickly because I'm almost out of time. Going back to that image before, what do the nearest neighbor classes look like again? So we have untransformed here like before, and naive, and we can see that global is doing a better job at keeping nearby dogs looking similar to the original dog. And here's one of the salamander. So with naive, we start getting things like snakes that are kind of similar in shape, but not the same, whereas global kind of keeps it thematically more sane. Okay, so takeaways, naive alignment does not work. We need to regularize to preserve aspects of the initial learned representation. It improves rich models, not so much simple ones. Improvement has to do with like global organization of concepts, and alignment is universal. That's it. Any questions?
Yeah, thank you very much for your talk. And we have a good amount of time for questions. So if there are people interested in hearing a bit more details, we have a microphone in the back, one here in the front.
Correct me if I'm wrong, but all these results are just for the images, right? It's not for the adjectives and all the other two data sets.
Yes. So this is all image-based. There has been some talk and preliminary experiments on text realignment, and that's really hard. Like, I don't know. Nothing is like, we're almost not working on it because like it's really more difficult.
I have two questions. First, is there also a possibility to do such kind of research in the audio situation, that you have an object, a violin, an object, something like that? And that's the first question. The second is, contrary to the audio situation, with images, the eye can be cheated enormously. So you could, in principle, just take 1/10 of, or even less of the information of the image and produce an image which the eye does not recognize the difference. Is this also used? And then allow me a third one. In my old days, in the old days, we were doing image analysis with wavelets, and this was extremely successful. Is this an issue today?
Okay, so audio, tricking the user, and wavelets. Those are the three questions. We haven't done audio, but this is pretty open still. These are really recent results. I think that'd be a fascinating thing to do. Basically, it seems almost like any data type would be kind of interesting to throw at a human and just see what the dimensions are and so forth. As far as trickery goes, hopefully I didn't misunderstand this too much. The things objects, so we're using just the images from things, and these are all very centered, like just a banana in the center. Like the effect of sort of some intentional or unintentional deception, I'm not sure. Like that's sort of outside of what we're looking at. And as far as wavelets, yeah, I love these basis methods too, but yeah, this is all just neural network stuff. So yeah, like a dictionary method kind of thing, or wavelets, yeah, sort of. I have not looked into it.
Thanks for the talk. Any idea on how to proceed without explicit regularization?
Can you elaborate? So you want it to be trained so that it's just naturally aligned?
I mean, apparently there is a distinction between the networks or the representation of images in the networks and our understanding of it. How can it, how can we prove it? Just, the answer can be no.
Sure. I mean, so the probing works, but you're saying do it earlier than probing, or yeah. So probing works. There's a lot of information in there. A thing you can look into, I believe someone has done this now, and it all kind of works, is to just have two tasks training at the same time, the triplet task and whatever task you're kind of interested in, and then things naturally get more aligned via this. Outside of that, nothing I'm aware of. It would be nice. It is sort of clunky that we just have to toss this additional task onto the network. It would be, but I mean, if you can come up with a way to naturally align a neural network via just some very clever regularization or training, that would be very interesting.
Maybe then I could ask a question. One, I thought that came when I was listening to your talk. I'm not an expert on images and machine learning, but I remember that some of these image classification models have issues when you would expect, if they make an error, that maybe the second or the third prediction is maybe reasonable, or that still, if you have a classification task, you get the first class that is predicted, that the second and third class don't really make so much sense. And there I remember that some people observed that for a human, you would expect, okay, if the model doesn't get it's a dog, then maybe it's a wolf, but the model makes error with this. So you think this could as well be an area where your way of aligning the representations could make a difference or could improve image models on?
So is your question, does alignment help with like these sort of zany suggestions during classification? Yeah, I'm not sure. Like it's look into it. It'd be interesting to see. So this last paper was just presented at NeurIPS just a few months ago. So yeah, it's all quite new.